Hello, and welcome to Chemistry with Dr. Clark. Today we'd like to talk about thermochemical equations. We would like to talk about pulling the molar enthalpy from the equation and then using it to calculate the heat that goes with reacting a specific amount of a chemical. Now, the equation that we're going to be using in the calculations today is going to be Q equals N times delta H bar. This symbol here at the end, the triangle and the H and the bar over the top, we do refer to that as delta H bar. Now, the little triangle, delta, means the change. So we're looking at the change in the H. The symbol with the line over the top, the bar, does indicate that it's a molar enthalpy. Now, the issue is that some textbooks do not use the bar. Some textbooks will just call this delta H. And the issue with that is that delta H can be either molar enthalpy or it can be just regular enthalpy, right? So we can call this molar enthalpy, or we can call it just regular enthalpy. This is the amount of enthalpy that comes from a reaction or some sort of change that involves only 1 mole of a substance. This is the enthalpy that comes from a reaction or a change with an undefined amount, right? So we could talk about how much enthalpy is related to melting an ice cube versus how much enthalpy is related to melting an iceberg, right? This number is going to depend on how much you have. So if you're only melting an ice cube, it's going to be a small amount. If you're melting an iceberg, well, obviously it's going to be a lot larger. It's the reason why we like the molar enthalpy, because that way everybody is starting with the same original amount. We're all starting with 1 mole of a substance. Okay, so they're different things. They have different names, but often textbooks will give them the same symbol. And the way that you're going to tell them apart, this one is going to be kilojoules per mole, energy per mole, and this one will just be kilojoules, just energy. Okay, so they're often a little hard to tell apart. So what some textbooks do is they put a line over the top, and they'll call this delta H bar to try and distinguish it from just regular delta H. Okay, so now when we're doing this, if you're talking about the number of moles, moles are always measured in mole. Now, the name for moles has an E on it, or an ES. The unit does not. So when you're talking about the unit for moles, it's just an MOL. And heat has a wide variety of units. So down here we were talking about kilojoules, which is the one we like the most. This could be in kilojoules. But we could also use it in joules or calories or kilocalories. There's a whole variety. The main key here is to have the units match. So if you're going to do heat in kilojoules, then you do your molar enthalpy in kilojoules. But if you've decided that you're going to do your heat in calories, then your molar heat would just be in calories per mole, right? Your units have to be consistent. Whatever you've decided to go with in your heat, it also should show up in your molar enthalpy. Okay, so this is the equation we're going to use. Now really, we should talk about a secondary equation because this calculation will require the number of moles. And in the world of chemistry, if we throw an easy question at you, the question will probably say, you had 5 moles of bromine, or you had 10 moles of water. But that's not typical, right? Usually when we're talking about chemistry, we don't want to talk about things in terms of moles. We want to talk about them in terms of mass. So you're going to have to be able to convert a mass into a moles, right? Because the formula needs a moles, but you are likely going to be given a mass. And that's because most things that we measure in the chemistry lab are measured in masses. So we do have a formula for this. Number of moles equals the mass divided by the molar mass. Okay, so this is my mass. This is my molar mass. And your molar mass comes from your periodic table. Okay, we consider the molar mass to be a given, even though you do have to go and find it. So let's say that we were going to talk about, sodium atoms. If you go to the periodic table and you look up sodium, underneath sodium there will be a number. What is the molar mass of sodium? Let me pull out my periodic table and take a little look. Sodium has a molar mass of 22.99. That's its molar mass. It has an atomic number of 11. And my periodic table does show you like a lot of other pieces of information. But if you have a very simple periodic table, the two pieces of information it'll give you is its atomic number, the number of protons, and your molar mass. And the units for your molar mass will be grams per mole. Which again kind of makes sense because it's a molar mass, right? It's the mass of 1 mole. So it'll be grams per mole. Your masses here will be in grams, and your moles, of course, will be in moles. So often we have to do this calculation first in order to figure out our moles, and then we use our moles in our calculation to figure out our heat. Okay, so not always, but for the most part, that's what we're going to have to do. All right, so let's take a look at a few problems. Okay, let's cover up the second one. So it says, how much heat will be absorbed when 18.2 grams of bromine reacts with excess hydrogen according to this equation? Now, this equation here is technically a thermochemical equation. It's got the chemical equation and it's got the heat or the thermo that goes with it. Usually though, when we give these to you, we don't usually have the heat off to the side or the enthalpy. Usually it's built straight into the equation. So perhaps what we should do for just a moment, we'll sidestep for a second. Let's build this straight into my equation. So in order to turn this into a true thermochemical equation, you just rewrite your equation. Br2 liquid turning into 2HBr gas. And we're just going to add this as either a reactant or a product. Now the way you're going to tell that is based on endothermic versus exothermic sign, right? If your delta H is positive, a positive delta H means that this is endothermic. In order for this reaction to happen, it's going to pull heat in from the outside. So if the heat is needed to make the reaction happen, if it's being pulled in, that means the heat really is a reactant. So I could add the 72.9 kilojoules to the reactant side, right? It's an endothermic reaction. Heat is getting pulled in. It's required for the reaction, so that's endothermic. So we can put it on the reactant side. Now, we didn't need to do that to do our calculation, but I thought I'd throw that in and talk about different ways of expressing our thermochemical equations. So now if we want to do this, we're going to use our little formula, Q equals N delta H bar. In order to find our heat, we are going to need to know the moles, and we are going to need to know the delta H bar. Now the delta H bar, let's talk about that first, because it's probably the easiest number to pull out of my equation. This is delta H. It's just in kilojoules. This enthalpy change goes with the equation exactly as it's written. So when you take one H2 and you react it with one Br2, you get 2 HBrs, and this is the amount of enthalpy that you get from it. Okay, you get 72.9 kilojoules. If I were to double the equation, if I were to use twice as much hydrogen, twice as much bromine, and get 4 times as much product, basically I've done the reaction twice, right? I've used up twice as many reactants, so I should get twice as much heat, right? The heat goes with the equation exactly as it's written. So if I had decided to double 2 of those, 2 of those, 4 of those, then I'd end up with twice as much heat, right? It's kind of like, think of having a campfire. If you put on twice as much wood, you will have twice as much fire, and you should get twice as much heat, okay? In order for me to turn this into this, I need to be able to say that this is per mole. I need to say that it's per mole. Okay, so let's get rid of these. Well, now that's an issue, because this delta H actually is per 1 mole of H2, right? There's a 1 in front of that H2. So this is already per mole of the H2. Same thing with the bromine, right? There's only 1 bromine. So this is per mole of the bromine. But it's not per mole of the product, right? You get this much energy per 2 moles of HBr, because there's 2 of them, right? So it's a delta H with a line on top when it comes to the hydrogen. It's the delta H with a line on top when it comes to the Br2, because for both of them it is per 1 mole, but it's not when it comes to the product, right? That's why in this equation it's not written as molar enthalpy change, because it's not true for every single one of the chemicals. Now, in this problem, there's only one chemical that's important. So as long as this is per mole for the important chemical, then I can ignore the rest. So if I look at this, it says how much heat will be absorbed when 18.2 grams of bromine. Bromine is the important chemical because they told me how much there was. So I need to make sure that this number is related to the bromine. Because there's only 1 bromine, then I can just put a line on top and say, hey, this is the molar enthalpy change per mole of bromine, right? Because the equation has 1. So this is like per 1 mole of Br2. Okay, that gives me my delta H. I'm ready now to just put it right in my equation. I do need the number of moles, but again, the problem doesn't exactly give me that. So I'm going to have to do a side calculation of mass over molar mass. Okay, so if I want the number of moles, I need to know the mass. This is my mass. It is 18.2 grams. And the molar mass is going to come from my periodic table. So if I look up bromine on my periodic table, bromine has a molar mass of 79.90 grams per mole. Now, that's the mass for 1 bromine. When you look in this equation, the bromine doesn't come by itself. The bromine comes in pairs. So if you're going to talk about a Br2 rather than just a Br, you've got to double that. So my molar mass is actually going to be twice 79.90. So my molar mass will be, let's pull out our calculator, 79.90 times 2 gives me 159.8 grams per mole. Now, if we're talking significant figures, when we're doing molar masses, if you're doubling something that has 2 decimal places, then you really should keep 2 decimal places. Okay, so now I've got my molar mass. That's 159.80 grams per mole. So my number of moles would be 18.2 divided by 159.8. That gives me 0.11389. Now, if we are looking for moles, you know the units are going to be moles, right? We talked about that just a moment ago. But if you wanted to do it through unit cancellation, you got a grams in the numerator and a grams in the denominator that'll cancel. That leaves you with 1 over moles. It's like the moles is in the denominator twice. It's in the denominator of the main fraction, but it's also in the denominator of the unit. So if you've got 1 over a unit, the 1 overs cancel, and it just gives you moles. Now, if we are talking about significant figures, some of you have to watch out for those. If I look at the 18.2, that has 3 significant figures. The molar mass, 159.80, has 5 significant figures. 1, 2, 3, 4, 5. And when you're dividing, you always go with the least number of significant figures. So 3 versus 5, my answer should only have 3. Now, you got to be careful of this 0 out in front. The 0 out in front does not count as significant, because if I covered it up, you can still tell me what that number is, 0.11389, right? The 0 in front is not really important. It's not significant to the number. You can leave it out. So if I want 3 significant figures, I'm going to keep the 1 and the 1 and the 3, but I'm going to get rid of everything else. So if I'm going to get rid of an 8,9, the 8 will round the 3 up. So my number of moles will be 0.114 moles. Now I have my moles. I have my delta H bar because it didn't really change. All I need to do now is put them in my formula. The amount of heat is 0.114 moles times 72.9 kilojoules per mole. And then if we haul out our handy calculator, we'll be able to say 0.114 times 0.114 times 72.9 gives me 8.3106. Okay, now if we talk units, I've got a moles and I've got a per moles. Moles in the numerator, moles in the denominator, they'll cancel. And the only unit left is kilojoules, which is what we expected, right? Heat gets measured in kilojoules. Now, if we do talk significant figures, like we said a second ago, the 0 doesn't count. So this has 3 significant figures. The 72.9 has 3 significant figures. So my answer should only have 3 significant figures. Keep the 8, keep the 3, keep the 1, get rid of the 0.6. Because 0 is less than 5, the 1 does not round up, it stays the same. So Q will be 8.31 kilojoules. Now let's talk about this making sense. This equation says if you reacted 1 mole of the bromine, then you should get 72 kilojoules. So 1 mole gives you 72 kilojoules. But you're reacting 0.1 mole. You're reacting only 1/10 as much, right? Instead of 1, you're reacting 0.1. So if you're reacting only 1/10 of the amount of bromine, then you should only get 1/10 of the energy. Now, I know it's not exactly 1/10, but if you took 1/10 of 72, that's roughly 7. And my answer is 8. That's pretty close to 7, right? So my answer does make sense. If you're only reacting 1/10 of the chemical, you should only get 1/10 of the heat. All right, let's move on to a second problem. If we move this one up a little bit, it's the same problem, right? It says how much heat will react when you have 12.7 grams of ethanol reacting with excess oxygen according to this equation. Now, once again, you don't need to rewrite the equation for this, right? You can just do the calculation. But since we have it here in front of us, I think it would be an excellent opportunity to take this energy and build it into the equation. So if I was going to do that, I'm going to rewrite the equation, C2H5OH liquid plus 3 O2 gases turns into 2 CO2 gas and 3 H2O liquids. Now I've got to decide, do I put the energy as a product or do I put it as a reactant? Well, if I look at this, this has a negative sign in front of it. We know that negative enthalpy changes, negative heats, always mean exothermic. So this is an exothermic reaction. It means that as the reaction happens, heat is being given off. So the heat is going out. If you're giving heat away, you're producing heat. If you're producing heat, your heat becomes a product, 1366 kilojoules. Now, considering we've done both problems, Endothermics ended up as reactants. Exothermics end up as products. Now the trick here is when you write a chemical reaction, we don't like negative signs in chemical reactions, right? Chemical reactions are all plus and plus and plus and plus. So we are going to say that it's plus. Okay, if we pull this back down a bit, when the delta H is by itself, the positive and the negative tell you whether it's endo or exo. Okay, that's your sign, right? This part of chemistry is all about recognizing the signs. So positive is endo, negative is exo. But when you put it in the equation, you don't need to use a positive or negative because now you're telling me if it's endo or exo based on reactant versus product. The minute I see it as a reactant, I know it's an endothermic reaction. The minute that I see it as a product, I know it's an exothermic reaction, right? I don't need to say positive and negative because I'm talking reactant versus product, right? Location is going to tell me endo versus exo. Okay, so to do this calculation, you really didn't need to do that, right? You didn't have to rewrite the equation. But like I say, it's nice to be able to see thermochemical equations expressed in more than one way. So for this problem here, it's the same as before. I've given you a mass of one of the chemicals and I want to know the heat. So again, I'm going to be using Q equals N delta H bar. So I need to know my number of moles. I need to know my molar enthalpy change. So if I look at my equation and I try and pick out my most important chemical, the minute they told me it was 12.7 grams of ethanol, that's what tells me the most important chemical. So this is my most important chemical. And as long as there's a 1 in front of my most important chemical, then I can say that this is the molar enthalpy because this much energy goes with, see if I can squeeze my mole in, goes with 1 mole of the ethanol, right? This becomes molar enthalpy if this energy goes with 1 mole of the important chemical, right? The delta H bars, they are the best because as long as you got a 1 in front of the important chemical, that's the molar enthalpy. Now, the number of moles, just like the last time, you're going to have to work for it. It is very rare for us just to give the moles to you, right? Mostly we will give it as masses and you have to calculate. So my number of moles would be my mass, 12.7 grams. Now for this one here, the molar mass is going to be a little bit more work, right? Because the formula for ethanol is a C2H5OH. If I want to know how heavy this is, because that's what a molar mass is, right? It's talking about the mass of the chemical. I need to know how heavy a carbon is and multiply it by 2 because there's 2 of them. I need to know how heavy a hydrogen is and multiply by 6 because there's 6 of them, 5 plus 1. And I need to know how heavy an oxygen is because there's 1 of them. Okay, so if you pull out your periodic table, carbons weigh 12.01, hydrogens weigh 1.01, and oxygens are 16. Right? If you look it up, 1 carbon weighs 12 and you've got 2 of them. 1 hydrogen weighs 1 and you've got 6 of them. 1 oxygen weighs 16 and, well, you've only got 1. So we pull out our calculator and we say 2 times 12.01 plus 6 times 1.01 plus 1 times 16. That gives me 46.08 grams per mole. And for Sig Figs, if all of these have 2 decimal places, then your answer should have 2 decimal places. But this now gives me my molar mass. So I can take this number and put it here. 46.07 grams per mole. If we pull out our calculator, 12.7 grams, which came from the problem, divided by 46.07, whoops, 12.7 divided by 46.07 0.08. I don't know how I miscopied it, but that's an 8. Gives me 0.2756 moles. Now, once again, if you are a significant figures person, 12.7 has 3 significant figures. 46.08 has 4, so my answer should only have 3. You always go with the least number. And the 0 out in front don't count. So my number of moles would be 0.276 moles. Right? If I am chopping it off here, if I'm getting rid of the 6 will call us the 5-2, round upwards. All right, so I got my moles. I've got my delta H bar. I can put them together and multiply them and find my heat. So my Q will be number of moles, 0.276 moles. My delta H is a minus 1366 kilojoules per mole. Now you'll notice that I did keep the minus sign. The only time that you're allowed to drop it is if you've written it as a product. But when I put it in this equation, that's not a product anymore, right? That's just a number that I've pulled out. So when you have a number by itself related to an exothermic reaction, you do need to keep the negative. All right, so we pull out our calculator one more time. 0.276 times a negative 1366 gives me a negative 377.016. Moles and moles will cancel, leaves me with kilojoules. And significant figures, 3 significant figures, 4 significant figures, so this should only have 3. 1, 2, 3, I'm going to cut it off there. Because the first number that I'm getting rid of is less than 5, then it doesn't round it up, it just stays the same. So minus 377 kilojoules. Now again, let's see if that makes sense. I am reacting 0.276 moles, basically a quarter of a mole. If you react 1 mole, you should get 1366. But if you're reacting a quarter mole, you should only get a quarter of that, right? And a quarter of 1366 divided by 4, about 341. I got 377, right? This is not exactly a quarter. That's why my answers didn't match up, but it does make sense, right? If you're only reacting a quarter of the chemical, then you should only get a quarter of the heat. All right, the first 2 examples, you were able to turn the delta H's directly into delta H bars, molar enthalpies. What about if the important chemical doesn't have a 1 in front of it? Then what do we do? All right, so let's take a look at that. So if we take a look at question number 3 here. How much heat will be released when 6.25 grams of chlorine reacts with excess phosphorus according to the following reaction? All right, now again, if we wanted to, we could take this energy and build it straight into the equation. Because it's a negative, it is exothermic. And so if we wanted to, we could add it to the product side. So we could just say plus 886.1 kilojoules, right? So you can either have them separate, or you can get rid of that and build it straight into the equation. Having a negative sign means exothermic. Having it as a product also means exothermic. Now, you don't have to do that in this problem, but I thought I'd point it out. Now, like the last 2, I'm going to be using Q equals N delta H bar. And because I am given a mass, I know that I'm going to have to do mass over molar mass. Okay, so now we had said that as long as your important chemical has a 1 in front of it, this delta H, regular enthalpy change, becomes the molar enthalpy change, which is what we need. Well, if I look here, chlorine is my important chemical, but I've got a 5 in front of it. I can't say that this is per mole if there's a 5. really what I have to say here is this is per 5 moles, right? Because if this is my important chemical, this reaction involves 5 moles. So this is the amount of heat I get per 5 moles, right? Per 5 of them. Now, that is a molar enthalpy. I just need to take that 5 and divide it out of my 886, right? I just got to do the math. So delta H bar will be 886.1 negative divided by the 5 is a minus 177.22 kilojoules per mole, right? Because if you divide the 5 into the 886, the 5 disappears from the bottom, and now it is just the kilojoules per mole. Now it's for just one of them. Okay? Now, there is an alternate way to do that. We'll do that in the next problem. But this is one way to do it, right? Instead of saying it's per 1 mole, you actually have a 5 here, so it really is by 5. So you have to divide the 5 out. Now, we do need to calculate number of moles. So my mass is 6.25 grams, and the molar mass comes from your periodic table. Now, this is where people kind of get tripped up a little bit. If I'm going to find my molar mass, am I finding the molar mass of the Cl2, or am I finding the molar mass of the 5Cl2? Should I be looking up how much a chlorine weighs and multiplying it by 2, or should I be multiplying it by 10? And the answer is just the 2. The numbers in front that are used to balance your equation are not part of the molar mass. Okay? Think of it like, let's say that you're a triplet. Okay, it's you and your 2 identical siblings. When we're talking molar mass, what I'm saying is, how much do you as an individual weigh? Right? So let's say that you're like 80 kilos. That's what I want to know. Per one of you, how much do you weigh? You wouldn't say, hey, we all weigh 80 kilos each, so it's a total of 240 kilos. Right? You walk in to get your driver's license, or you walk into the doctor's office and the doctor is like, so how much do you weigh? Right? You wouldn't say, collectively, the 3 of us weigh 240 kilos. Right? That's not how it would work. And it's the same thing here with my molar masses. Right? This is meant to be the mass of just the chemical, not the number in front. So if I'm going to do this, it's only going to be 2 times the molar mass of a chlorine. Chlorine has a molar mass of 35.45. So that would give me 70.90 grams per mole is my molar mass. Okay, that trips people up a lot. That 5 out in front, or whatever number's out in front, they're like, should I include it or should I not? When it comes to molar masses, you don't. Okay, so if you got your molar mass, that's 70.90 grams per mole. If we pull out our calculator, 6.25 divided by 70.90 gives me 0.08815 moles. If we talk about significant figures, the 6.25 has 3, the 70.90 has 4, so this number should only have 4. Now you already know that this 0 out in front don't count. Turns out that this 0 in front don't count either. Zeros in front of a number do not count for significant. So if you have 3 versus 4, you should only have 3 significant figures in your answer. That would be the 8, and the 1. That 5 should disappear. Because the first number that I'm cutting off is a 5, that means I have to round up. So my number of moles would be 0.0882 moles. All right, so I've got my delta H bar right there. I've got my number of moles right here. All I need to do is multiply the 2 together, and then I've got my heat. So my Q will be 0.0882 moles times a negative 177.22 kilojoules per mole. So my Q is going to be 0.0882 times 177.22 negative gives me a minus 15.6308. Moles and per mole cancels, leaves me with the kilojoules. Now, let's talk Sig Figs. I did Sig Figs here, but I forgot to do my significant figures here. The 5 is a counting number. Okay, that's exactly 5. So technically it's 5.00000000, right? As many zeros as you want. The 5 has an infinite number of significant figures because it's exactly 5. So if you've got 4 Sig Figs divided by an infinite number of Sig Figs, your answer should only have 4. So when I did this, I should have kept the 1, the 7, and the 2, but I should have gotten rid of the last 2, right? Because I should have only had 4 Sig Figs. So if I come back over here, 3 significant figures versus 4 significant figures, my answer should only have 3. So I'll keep the 1, I'll keep the 5, I'll keep the 6, but I'm going to get rid of everything else. So my heat is going to be a minus 15.6 kilojoules. All right. Let's say that we'd like to do a similar problem, but we'd like to do it a slightly different way. The way that I'm going to do it here, we'll still divide this by whatever number is in front to clean that up, but it will eliminate this bit of confusion here as well. Okay, so it's a slightly different way of thinking about it, but we are going to do the exact same problem. So the problem says, how much heat is transferred when 45.6 grams of ammonia reacts with excess oxygen according to the equation? Okay. Now, I believe that in the very first problem, I talked about how if you doubled all of the numbers, you had to double the heat, right? It's like a campfire. If you put in twice as much wood, you should get twice as much heat. But let's say instead of doubling everything, I halved it. If I only used half as much of the reactants, I should only get half as much of the products, and I should only get half as much heat. Right? Think of your campfire. If you have a campfire that's only half as big, you should only get half as much heat from it. Well, ammonia is my important chemical. I would really like to have a 1 in front of the ammonia. So I can do that. If I divide this by 4, 4 divided by 4 will give me 1 ammonia. Okay, so I'm deciding to use 1/4 of the amount of ammonia. But if I'm only going to use 1/4 of the amount of one reactant, then I have to use 1/4 of the amount of the second reactant. I'm only going to get as 1/4 of as much of the products, and I'll only get 1/4 as much of the heat. Right? Up here, I had a 5 in front of the chlorine, so I divided the heat by 5. Here I have a 4 in front of the ammonia, so I'm dividing it by 4. Right? I'm doing the exact same thing. I'm just thinking of it slightly differently. Right? Here I'm thinking of it as, let's quarter everything so that way I can see I have a 1 in front of the ammonia. And if I have a 1 in front of the ammonia, it eliminates the problem of do I include the number in front in the molar mass or not, because the number in front is a 1 now. It basically disappears. Right? So it prevents you from running into a few snags later on. Now for this, I'm still going to do divide by. Right? So my deltaH will be 1172 divided by 4, which gives me 293. Was negative, it is negative. And because I've rearranged this equation so that there's a 1 in front of the important chemical, this now gets a bar, and it is now kilojoules per mole, because it is for 1 mole of the important chemical. All right, so I am eventually going to use Q equals N delta H bar. But again, before I get there, I have to get this mass and turn it into moles. So N equals mass over molar mass. My mass is 45.6. The molar mass comes from the ammonia. And now I don't have to worry about, do I include the number in front? Because the number in front is a 1, right? 1NH3. The 1 in front doesn't change your life at all. So you got one nitrogen, and you've got 3 hydrogens. A nitrogen weighs 1401, and a hydrogen weighs 1.01. So if we pull out our calculator, 1 times 14.01 plus 3 times 1.01, that gives me 17.04 grams per mole, and that's my molar mass. Okay, let's talk significant figures. Here, when I divided this by 4, you had 4 significant figures divided by a 4, which is a whole number, right? It's a defined number. It is technically 4.0000000. Okay, so this thing has an infinite number of decimal places. So it has an infinite number of significant figures. 4 sig figs divided by an infinite number of sig figs should have 4, but this only has 3. Now, this is unusual. Every problem we've done until this point, we always had a giant number that we had to cut down. This number doesn't have enough sig figs. I need to add on to it. So what I should do is put a little decimal 0, right? Because 293 decimal 0, that will give me 4 sig figs. For my molar masses, 2 decimal places, 2 decimal places, 2 decimal places. Okay, so 17.04 grams per mole. Pull out our calculator. 45.6 divided by 17.04 gives me, now, 2.676056, and that's all I've written down because, well, my hand got tired, right? Because this number goes on forever, and I know that if I'm going to do significant figures, that it's going to get chopped off. 45.6 has 3 sig figs. 17.04 has 4, so my answer should only have 4. So keep the 2, keep the 6, keep the 7, get rid of the rest. You're getting rid of 6, that's going to cause your number to round up. So 2.68 moles. Got my moles, got my delta H bar. If I put them together now, that'll give me my final answer. So Q equals 2.68 moles times a negative 293 kilojoules per mole. Moles and per moles cancel, so my final unit will be in kilojoules. And I'll get 2.68 times a negative 293, and that gives me a negative 785.24. The only unit left is kilojoules. 3 sig figs, ooh, I forgot that's 0, right? I determined that I'm just going to leave it out, right? We said here 4 sig figs you had to put on to 0, so 4 sig figs put on to 0. So 3 significant figures, 4 significant figures, my answer should only have 3. So keep the 7, keep the 8, keep the 5, get rid of the rest. So the amount of heat will be a minus 785 kilojoules. Now, if the original equation had a negative heat, that means it's exothermic. Whether you react a lot or a little, it's still going to be exothermic, right? So it's still going to be a negative here at the end. All right, I hope that helps you understand working with thermochemical equations and using the delta H given in the equation to calculate the heat that goes with reacting a specific amount of a chemical. And as always, thank you for joining us here with Chemistry with Dr. Clark.